Welcome to my blog on big data and cybersecurity. My name is lipyeow-sec. I'm a computer scientist and educator and a software engineer. And today I would like to actually chat a little bit about RAG and basic information retrieval for LLM agents. I've been kind of working on agents. I've been working with Cloud Code, especially. I really enjoy using Cloud Code. And there was a bit of a controversy maybe several months ago when people realized that Claude Code wasn't using a RAG, right? Now, what does a RAG mean, right? It's retrieval augmented generation. It means that it's not storing the code repo that is working over in a vector database and retrieving snippets out of it when it actually does all its coding. Um, Either trying to understand the code or trying to help you with fixing code and generating code. So there was a bit of a controversy in the internet, and there's different blogs that actually talked about some of this. I'm not going to go into those in detail. I do want to show you quickly what I'm talking about. In particular, in this case, not to search over code, but to search over documentation. And I'll show you how actually Claude Code does it, right? So for example, if I ask it a question, there was a new feature that came out recently called sub-agents. I haven't used it yet, and maybe I want to find out a little bit more about it. I can ask, how would I use the sub-agent feature? I'm going to keep it vague. I'm not going to tell it I'm actually asking about Claude Code itself, but it seems to go figure out most of the time. So let's see what happens. It will think for a few seconds. It does its first web fetch, and I see a second web fetch. It's for Claude Code docs.map.md file. Very interesting. It looked at the first web fetch is probably a redirect, so it's probably shouldn't count that. In this case, oh, interesting. It failed to fetch the sub-agents. I think it didn't quite get it this time, so actually I had to look through a few times. And previously I've ran this, it just managed to kind of go right through. But this is what we're dealing with. These LLMs are non-deterministic, so you do get non-deterministic behavior. But finally, it did find the right document. And then it actually got me the right answer, right? And it looks decent. Probably what I need to get started. I can dig a little bit deeper, right? But what I want to actually get to is how Cloud Code actually does these fetching. I mean, less this non-determinism from the model, right? So there was a blog that came out of Milvus, some of the Milvus folks, and it talked about why I'm against Cloud Code's grab-only retrieval. It just burned too many tokens. You can read this. I think this is extremely informative blog. Thank you, Chenny Zhang, for actually doing this. And lots of interesting content. It talks about how to use different strategies for chunking the code data, like using an AST-based chunking method before actually converting each chunk to embedding models. It had a way to detect which chunks change using Merkle trees to actually quickly figure out which chunks has changed and which chunk needs to be re-indexed, in the sense that you would get to rerun it through the embedding model to get the vector and then update the vector within your vector index. So really good information. You should take a look at it. This is the blog that actually first pointed to this Claude Code docs map.md file. Again, it's the same pattern advocated by the LLMs.txt recommendation for websites, right? And if we go look at this file, I think there's something interesting to learn there, right? So this is the Claude Code documentation map. It does say this is auto-generated. This is not generated by hand, and it's purely for LLM consumption, right? And you see it actually has a nice document structure. It actually gives you links to all the underlying documentation with a short blurb that gives you a semantic description, right? And this semantic description, from what they say up here, is that it just takes the outline or the headers from the doc and puts it here. And that is, if you structure your docs correctly, that's enough for the LLM to reason about this and to actually be able to search for the documentation, right? So this seems very reasonable, and you see it's quite long. The map actually goes through, I guess, the top level documents in the Claude Code documentation structure, right? And It is pretty effective most of the time that I search. It actually brings back the right information within one or two fetches, and it can then actually generate the answers for you. And before we dismiss this as sort of a, hey, this is so simplistic and hierarchical, I think there's some cleverness in this simplicity here, right? If you think about it, this doc, this map, actually resembles the top node of a classical B tree or B plus tree index in databases. And B tree indexes have been used in databases for many decades, very effective, extremely performant, right? Um, and let's draw some similarities here, right? In a B plus tree index, the top node contains kind of the top level partitioning of the data into different partitions. In this case, with the B plus tree index, it uses keys that have total ordering, like integer keys or floating point, or even strings, anything that have total ordering to them, so that you can partition it into ranges, right, that are totally ordered. And then you can actually traverse down the tree to get to the final page or the final node that contains all the data that you want, right? Um, and in most practical cases, the B plus trees are actually very shallow, right? At most one or two levels, in most practical use cases. But the fan out is huge. Fan out is like in the hundreds, sometimes even thousands, right? And that's sort of the pattern that we observe here as well, right? With this Claude Code map, right? It's likely a pretty flat structure, but very effective in kind of pruning the search space, right? The key difference though is that in the map.md file, right, there's no total ordering of these semantic keys. Let's call them semantic keys, right? These blurbs that represent these semantic keys, right, for that particular link, right? So it doesn't have that total ordering, which means you have to structure your semantics in a very nice way. But that's something that, again, LLMs can actually help us with in many ways. But if you do have hierarchical structure, it does work pretty well. What does this mean for us, right? Again, if we are building agentic systems, right, that needs to retrieve unstructured or semi-structured information, this is yet another way to actually do it. And let's actually go back and actually wrap up, right? Because I think the main takeaway for me is that, well, at least for unstructured and semi-structured data, there are two patterns emerging, right? So we have vector search, which was the RAG-based systems, right, where the embedding models map semantics to vector space in the high-dimensional embedding vector space. And actually, that still falls under classical information retrieval that uses vector space, right? It's just that you're using embedding models to map into the vector space. And then versus this map model, which actually resembles, like I say, it resembles P plus tree search patterns, right? Except that it has got non-integer or keys that don't have total ordering, right? But it is pretty effective, and there's a certain simplicity to it. You don't have a lot of issues with updating of the vectors of the embedding model, embedding vectors, and then updating the HNSW nearest neighbor index in the vector search database, right? So, and it does work. And in the case of Claude Code, because the baseline was so low, like prior to Claude Code, I had to go to the website to search for Claude Code documentation, look for subagents. It might take me a few rounds of searching before I actually get to the web page that I want with the right documentation. Then I got to go pass through the entire page to look for the bits that I want, right? And so even Claude Code, even with its non-determinism of making mistakes and kind of fixing itself and doing the fetches, it still brings me the right information back in a much shorter amount of time. May not be the most optimized, may not be snappy, but that's an optimization problem we can solve as a second pass. Anyway, hope you enjoyed this episode. I'll see you next time.